Students, we start with chapter Gravitation. In this chapter we discuss how gravity plays an important role in day-to-day life and how gravitation acceleration is to be changed when we go latitude, above the surface of earth, below the surface of earth. Okay, and what is the gravitation acceleration due to rotation of earth. So in this chapter we discuss totally about the gravitation acceleration, how gravitation acceleration is to be changed or vary from place to place. So first we start with universal law. Universal law of gravitation. So this law is applicable everywhere in the universe. That is why it is called universal law of gravitation, and it states that whenever two objects are separated at a finite distance, so both the object experience force. This force is called here force of gravitation, and in day-to-day life we cannot observe this force because its value is to be quite low. We cannot be experiencing day-to-day life, but this force is applicable. Okay, so universal law of gravitation states that whenever two objects, for example m1 mass of first object and m2 this is mass of second object, so when both the objects are placed at separate distance r, so one force of attraction is acting between two objects. This is said to be F. Okay, and from first to second this is F12 force, and for second to first this is F21 as per Newton's third law. So force on first object due to second is to be represented by F12. Similarly on second object due to first this is F21, and total force is to be denoted by F. So this law states that force of attraction, not repulsion, force of attraction is directly proportional to product of mass and inversely proportional to square of distance between them. When we combine these two identities, so F is equals to, here constant is to be G m1 m2 upon r square. So this is the value of force of attraction between two bodies, or we can say two objects. Okay, now every constant have some specific value. So here capital G having value 6.67 into 10 raised to the power minus 11. If we come to unit part, so Newton meter square upon kilogram square. So this is Newton into meter square upon kilogram square. This is the force of attraction. Okay. Next we take one example in order to understand how this force of attraction plays in day-to-day life. So we take one example. Suppose like m1 mass of one person is suppose 50 kilogram. Similarly for second person mass is suppose 50 kilogram, and both the person having distance between them suppose 1 meter. Okay, like in classroom two students are separated by a distance of suppose 1 meter. So how much force experienced by us? So now we use the identity F is equals to G m1 m2 divided by r square. So F remains same, G 6.67 into 10 raised to the power minus 11, 50 into 50 divided by distance square, that is 1. So this becomes 6.67 10 raised to the power minus 11. So minus 11 and this is 20. This point is to be removed further, so it becomes 100. 20 here cancel out. Now 667 into 25 and with power minus 11. That means 0.00000. So this value is, because of 10 to the power minus 11, very small. So we cannot be observed in day-to-day life. But there must be some attractive force between the two objects. So this is the universal law of gravitation and it is applicable for everywhere. Next we come to how the acceleration varies from place to place. So first of all we find the relation between capital G and small g. Then we find out the variation in g value. Relation between capital G and small g. So in order to understand this concept, we take Earth. Let us consider Earth in shape of sphere of radius capital RE and its mass is ME. Okay, since Earth is to be solid, so it is to be represented by sphere in dots. Okay. Now suppose one object of mass M is to be placed on the surface of Earth. Okay. So here two forces act on this object M. First of all, because we have two masses and separated by a finite distance, so first of all force of attraction between them from universal law, F is equals to G, mass of first object, this is mass of Earth, into mass of second object M, and this is to be separated by a distance RE square. Equation number first. Second one, this object is to be placed on the surface of Earth, so it also experiences one force. This is F is equals to mass into gravity, that is gravitation and acceleration. So two forces act on this object. Now we have to compare equation first and second. So G, this equals to M into G. Now M to M cancel out. So we get the relation G is equals to G ME upon RE square. So this is the relation between small g and capital G. Okay, now we see what is the differentiation capital G versus small g. First difference we have already know in numerical value. Its numerical value is 6.67 into 10 raised to the power minus 11, while small g having value standard value 9.8 meter per second. Another one difference, this is universal constant. That means never change its numerical value. So this is universal. And this it varies from place to place. Okay. Third one is it is scalar quantity, that means it shows only magnitude part, but small g it is to be vector. So this is the three key difference between capital G and small g, and you always keep in remember gravitational constant capital G and this is gravitation acceleration. Okay. So on the basis of this G is equals to Gme upon Re square, now we see how small g varies from place to place. When we go above the surface of Earth, if we go below the surface of Earth, so how small g, that is gravitation acceleration, is to be changed. next we see how gravitation acceleration is to be varies. First we take above the surface of earth. Okay, what happen when we go above the surface of earth and how small g is to be varies. So again we have to take earth is in sphere. So let us consider earth in shape of sphere of radius RE, radius of earth, and its mass is ME. This is mass of earth. And again we have to make dots. This indicate earth is solid. Now here our object is to find out the gravitation acceleration above the h height from the surface of earth. So surface of earth, this is to be denoted by small g, and above h height it is to be denoted by g dash. So in this situation we find g and g dash. Okay, so as we know, from surface of earth, small g is equals to g me upon re square, equation number 1. We have just calculated before this derivation. So g is equals to gme upon re square. Now if we go above the surface of earth, so above the surface, this is to be represented by g dash. G remains same, mass of earth remains same. Now change only distance part. Now it includes radius of earth plus h height. So instead of re we have to write here re plus h square, say equation number 2. Now we have two equations, and with the help of these two equations we have to find what is the value of g dash. So for this we have to divide equation second by equation first. So equation second is here g dash, this equals to gme upon re plus h whole square, and this factor is to be divided by g. So we have gme upon re square. Now gme to gme cancel out. We have g dash upon g, this equals to re square upon re plus h whole square. Okay. Now we simplify this. So in order to simplify here, we in denominator part we use the binomial theorem. So g dash upon g, this equals to re square take common, 1 plus h upon re square cancel out, and denominator part is to be shifted in numerator. So g dash upon g, this equals to 1 plus h upon re square with inverse. Okay, so g dash is equal to g 1 minus 2h upon re. So this is the value of gravitation acceleration above the surface of earth. Now what we may conclude from this, if g dash is equals to z, then we can say gravitation acceleration is to be same surface as well as h height, but here some parameter is to be minus. That means in g value some numerical value is to be subtract. That means this shows gravitation acceleration is to be decreases as we go above the surface of earth. So this is the first conclusion. Next we see how gravitation acceleration is to be changed due to shape of earth. second case we take here, due to shape of earth. So actually we know our earth is in shape of ellipse, but for calculation purpose we take the sphere. So actually it is ellipse or oval shape, and in oval shape obviously if we compare the poles and equator part, so equator distance is more as compared to poles. So first of all we make one circle inside this, so that our previous calculation is to be utilized. Now this is again, we have radius of earth. Okay. Now this remaining portion. So experimentally it is found that this remaining portion on both sides, this is to be 21 kilometer more. That means if we compare the pole radius and equator radius, so equator radius is more than 21 kilometer, and this is to be utilized in order to find the gravitation acceleration at poles and equator. So for if we calculate the poles, so this is treated like a gravitation acceleration at the surface of earth. So gravitation acceleration at poles, this equals to gme upon re square, equation number 1. If you find out the at equator, so gravitation acceleration at equator, this equals to gme upon re plus 21 kilometer square. Say equation number 2. Now if we compare equation first and second, so if we compare equation first and second, so we may conclude that because of denominator part, resting numerator part remains common. So this shows here gravitation acceleration at poles is more than gravitation on equator. The reason behind it, in equator part denominator is to be more. So when we divide it, the value is to be very small. So this also states that poles gravitation acceleration is more at poles as compared to equator. So if we have suppose 2 kg of gold, but when we weight on poles, so maybe 2.1 or 2.2 as compared to equator, and equator it may be 1.9. So there is a less difference. And lastly come to gravitation acceleration at below the surface of earth. So below the surface of earth, again we have to make one sphere of radius re. Radius remains same throughout the sphere. If we take suppose, we have to find the gravitation acceleration at this point, and this is the value is suppose h, where we find out the gravitation acceleration g dash, and again surface, this is to be denoted by g. Okay. As we know, our earth is in solid form. That means here we use the density concept. Density is equals to mass upon volume. So mass of earth divided by volume, and volume is to be treated 4/3 pi re cube. So mass of earth in terms of density, density into 4/3 pi re cube, equation number 1. So in this derivation, mass of earth is to be represented by rho 4/3 pi re cube. Again we find at surface G is equals to GME upon RE square. We have already calculated this. Now mass of earth is to be replaced. G RE square remains same. Mass of earth is from here in terms of density. So density 4/3 pi and RE cube. So this cancel out. We have only G rho 4/3 pi and RE. Say equation number 2. Similarly, if we find the below G dash, so we can say G remains same, rho remains same, 4/3 remains same, pi remains same, this RE. Now remaining part is here RE minus H. So this is to be replaced by RE minus H, equation number 3rd. Now again equation 3rd is to be divided by equation 2nd. So this becomes G dash upon G. G to G cancel out, rho to rho cancel out, 4/3 to 4/3 cancel out, pi to pi cancel out. So remaining we have RE minus H divided by RE, or 1 minus H upon RE. So if you find out the G dash, it becomes G 1 minus H upon RE. Again we see the approximate result. If G dash is equals to G, then we can say value remains same, but still some term is to be subtracted. That means if we go below the surface of earth, so again gravitation acceleration is to be decreased. And if we talk about the center, so in order to calculate the acceleration at center, so what we can say, height and radius, this remains same. So if we replace here H equals to RE, so we find G dash is equals to 0. That means at center part it is to be 0. So overall we may conclude from here, either above the surface of earth, below the surface of earth, gravitation acceleration is to be decreased, and at center its numerical value is to be 0. Thank you.